Good morning. I guess starting a conference at 8:30 is one of the earliest conferences ever on this planet. So, but since the agenda is fairly booked, maybe we should start at least. Since we have most probably the giants of IPv6 here, so let's do this as a press conference instead of a conference itself, so we can talk to each other and maybe start to think about what we should do next year in order to get the NFV and SDN folks to listen to what we are working on, because without our work, I guess their work will be just reinventing legacy. That's a side note, but we'll fix this. So. Very pleased to have one of the brilliant ladies we've discovered lately from Huawei, Tina Tsou. I don't have your CV printed here, so maybe you don't want to release any private information about yourself, but maybe I'll let you introduce yourself. Okay? Please. Is your presentation up there? So that will be the Open v6 architecture. Tina.
Hello, my name is Tina Tsou. For those of you who don't know me, I'm a technical lead and principal engineer at Huawei, as well as the Northbound Interface Working Group Vice Chair for the Open Networking Foundation. Diego Lopez, the co-author of this presentation, is not here with us today, but Dr. Lopez is senior technology expert at Telefonica I+D, the research and development company of the Telefonica Group, and in charge of the technology exploration at their global CTO unit. Telefonica and Huawei shared a common belief that DevOps adoption is critical to the rate and scope of the worldwide IPv6 adoption. Today, we would like to share with you how SDN can smooth the DevOps transition to IPv6. Let's start by reviewing some key IPv6 industry dynamics. One of the reasons why DevOps is such an important arena for IPv6 is because its evolution leads to continuous operations. SDN IPv6, or Open IPv6 as we call it, will play an important role in helping DevOps achieve the continuous integration, delivery, and deployment behind continuous operations. But when someone mentions IPv6, this is the DevOps reaction. Why is that? That has been their reaction because, so far, the transition to IPv6 has been very challenging. The implementation of IPv6 is complex because IPv4 and IPv6 end users and applications will coexist during the IPv6 transition period. This leads to a variety of scenarios that must be supported during the transition period. IPv6 end users accessing IPv6 Internet via a service provider's IPv4 network infrastructure. IPv4 end users accessing the IPv4 Internet via a service provider's IPv6 network infrastructure. IPv4 end users accessing the IPv4 Internet, and IPv4 end users accessing the IPv6 Internet. So there are some existing IPv6 transition mechanisms, but no one can cover all of these scenarios. So the cost is high because the network needs to be upgraded, which leads to a huge CapEx and OpEx. There is a lack of native IPv6 applications, and IPv6 is proven only as a solution to the exhaustion of IPv4 addresses. Finally, the organizations are taking this medicine by when they have to, because the user experience has not been great due to a lack of IPv6 application. As of last week, there were about 120 million v4 IP addresses available across all of the regional Internet registry. That number may seem like a lot, but it is really very small. This chart shows exactly how fast the need for new IP addresses is growing and how small the supply of 120 million IP addresses compares to the demand for new IP addresses. Since 2009, we have 8 times the number of Internet-enabled devices, and within the next few years, we will be adding over 1 billion devices per year. In spite of demand for IP addresses outstripping demand, our industry has found ways to keep doing business. IPv4 readdressing and address reuse are strategies that are widely deployed out of necessity. But they are temporary solutions that are full of issues, and they fail to solve the fundamental problem. IANA has run out of IPv4 addresses. The need for new addresses growing fast, and as we all know, IPv6 is a complete and thorough solution to the problem. I'm happy to report that after many years of very slow adoption of IPv6 took off in 2013. This graph shows the percentage of users that access Google over IPv6. Starting from a small case of only 1% of users in 2012, adoption tripled in 2013 to 3% of users using IPv6. This is a stylized version of technology adoption cycle described by Geoffrey Moore in his book, Crossing the Chasm. Until now, only innovators and early adopters have deployed IPv6. If adoption of IPv6 continues to accelerate, and with a little help from DevOps, IPv6 will cross the chasm into the mainstream. In that next phase of adoption, where the early majority deploys, it will be considered very cool to have implemented IPv6. Now that we have established the need for IPv6 and the challenges in making the transition, let's look at a solution for meeting the challenge. That solution is Open IPv6, powered by SDN. Open IPv6, powered by SDN, is a super solution for the DevOps migration from IPv4, and these are the reasons why. Open IPv6 allows for a smooth migration with a unified mechanism. It enables DevOps by providing extensibility via programmability, by integrating deployment and operation into the implementation, and by streamlining OSS. IPv6 powered by SDN lowers the deployment and operational costs for decoupling the data plane and control plane, and by providing unified data plane devices. It also nurtures the development of native IPv6 services through the availability of open northbound APIs. And Open IPv6 reduces operational complexity and risk via the unified data plane, which adapts to different transition scenarios. This slide shows the architecture of Open IPv6. The key features of Open IPv6 are the coupling of the data plane and control plane, the presence of northbound APIs for services needed to manipulate the traffic. In addition, the approach is flow-based and IPv6 routing compatible. Notice the edge device in the data plane is flow-based, and the control plane and network services are removed from the device. These two factors help to unify the data plane and improve its extensibility. Also, notice that Services such as OSS and IPv6 transition services are deployed at the application layer. All of these features bring multiple important benefits to DevOps organizations who implement this architecture. Different IPv6 transition scenarios can be supported. IPv6-based services and different scenarios are supported by uniformed equipment. Open IPv6 will accommodate future IPv6 services, and the architecture is unified with any IPv6 migration path you take. Simply put, an open IPv6 architecture powered by SDN offers the promise of greatly reducing the complexity and cost of an IPv6 transition. Now that you understand the structure of an open IPv6 architecture, let's look at how it works. Starting from the bottom, the data plane is flow forwarding and IPv6 routing compatible. It enables the application to manipulate the traffic. In grid, the controller handles packet-in events. It provides open APIs for applications, and it enables applications plugin and enables applications to program the data plane. The northbound interface, represented by the arrow, enables the application to manipulate traffic via northbound APIs. Finally, at the top, the application modules provide user functions such as OSS, third apps, and IPv6 services. This slide shows Open IPv6 in action, processing flow-based services. The blue line represents the first packet of an unknown flow, or first request of the subscribe. It shows the first packet of an unknown flow is sent to the controller and triggers policies delivered to the data plane. The gold line represents the first packet of an unknown flow. It shows how the data plane creates entries for the flow and how subsequent packets are forwarded based on the data plane policies. We suspected that seeing Open IPv6 in action in PowerPoint diagrams was great for convincing marketing people, but not terribly convincing to experienced DevOps professionals. So we decided to collaborate with others in the industry and truly bring Open IPv6 to life. We brought Open IPv6 to life in 3 live demonstrations. First, a rapid deployment demo where each deployment was completed in 1 day. Second, a demonstration showing how simple it is to configure one unified mechanism. And third, a demonstration of how OpenSDN-powered IPv6 is. This demo features end users and apps using IPv6 and or IPv4, and how quickly new services can be provisioned using the northbound APIs. The demonstrations I'm about to review with you were conducted with the help of a convenient tool for configuring this Lightweight 406, MAP, CRD, and other 6RD and other services. We are proud to say this tool is also the world's first SDN mobile app. You download the Android app from Huawei or Google Play. If you are an iPhone or iPad user, you can download the iOS app from Huawei and soon from Apple's App Store. Now, let's look at the 3 live demonstrations starting with rapid deployment. The demo was conducted at the Etsy Network Function Virtualization meeting last April 2013, where we provide the IPv4 and IPv6 Internet access to more than 270 participants who visiting the Internet via our Open IPv6 implementation. All the feedback we received was positive. There was no user complaints, and participants said they experienced fast network performance. The simple management and operation demo was conducted at the Global Open Networking and SDN Conference in August 2013, where we provide the IPv4 and IPv6 Internet access to more than 800 participants who visited the Internet via our open IPv6 implementation. This featured the simplicity of configuration with only one mechanism used for different kinds of Internet access scenarios, such as v6 host visiting v4 Internet, v4 host visiting v6 Internet via v6 network, etc. Again, the feedback was very positive. The third experiment was deployed at the NBI Leadership Roundtable and ONF NBI Working Group meeting last November and provided the IPv4 and IPv6 Internet access to about 200 participants who visited the Internet via our open IPv6 implementation. This demo showed the benefits of fully decoupled control plane and the application layer when deploying IPv6. With the network services and operations are all acting as applications, we showed how they could be enabled and disabled online. We expect this to help rapid service deployment and collaboration between services and operations, key capabilities for DevOps implementation of IPv6. I wish I could have more details about our experience in building the live demos, but unfortunately we are short on time, so I would like to summarize by saying that the epic industry migration to IPv6 is accelerating. SDN-powered IPv6 makes the transition simple, rapid, and open. And implementation by DevOps is key to the success of IPv6 in the future. And for DevOps professionals pondering the future of IPv6, remember the words of Alan Kay. The best way to predict the future is to invent it. Before I step down, I would like to bring IPv6 to life in another way with a video featuring Dr. Lopez. Enjoy. I hope it's coming.
Hello everyone, my name is Telefonica Research. Welcome to this video. I'm at the Huawei campus and we will discuss the Telefonica and Huawei joint innovation of SDN on SDN IPv6 and show how we are submitting the use case to the Open Networking Foundation. Following this, Justin Dutzade, CTO and Vice President of Technology Strategy at Huawei, will discuss how SDN IPv6 is being deployed at the Santa Clara Huawei campus and how SDN IPv6 Internet access is provided for the network function virtualization second meeting. The transition to IPv6 technologies is gaining momentum on a global basis, basically because of the lack of IPv4 addresses, though there are a number of other technological reasons for transitioning to IPv6. However, IPv6 requires costly end-to-end network upgrades, and while IPv6 transition tools exist, they introduce a host of new issues. SDN provides a programmable platform for service deployment, which can also be used to reduce the new issues associated with IPv6 transition.
Wait a minute.
Sorry about that. Let's replay. No sound?
Research. Welcome to this video. I'm at the Huawei campus and we will discuss the Telefonica and Huawei joint innovation of SDN on SDN IPv6 and show how we are submitting the use case to the Open Networking Foundation. Following this, Justin Dutzade, CTO and Vice President of Technology Strategy at Huawei, will discuss how SDN IPv6 is being deployed at the Santa Clara Huawei campus and how SDN IPv6 Internet access is provided for the Network Function Virtualization second meeting. The transition to IPv6 technologies is gaining momentum on a global basis, basically because of the lack of IPv4 addresses, though there are a number of other technological reasons for transitioning to IPv6. However, IPv6 requires costly end-to-end network upgrades, and while IPv6 transition tools exist, they introduce a host of new issues. SDN provides a programmable platform for service deployment, which can also be used to reduce the new issues associated with IPv6 transition. We have defined and demonstrated IPv6 transition technologies in an SDN-enabled network. The idea is based on deploying several OpenFlow switches at the edge of the network. Though these OpenFlow switches, currently based on OpenVIF switch, have a simple, straightforward extension to support IP in IP tunnels. The OpenFlow switches process the incoming packets based on flow tables delivered by an IPv6 transition app via the SDN controller. This constitutes an example where an application controller interface has been defined to enable the IPv6 transition app to communicate with the SDN controller, bringing a standard interface to instruct the SDN data plane on how to apply IPv6 transition technologies. The abstracted view of the application controller interface for IPv6 transition is shown here. The controller provides an interface to the IPv6 transition app, enabling to modify traffic processing using OpenFlow. Specifically, the controller provides an OpenFlow driver that enables the IPv6 transition app to instruct all SDN-enabled equipment how to treat traffic, thus making it possible to flexibly choose the particular transition mechanism to be applied and to select the parameters governing it. The processing shown for this case is generic. A flow can be identified by part of the layer 2 to layer 4 packet header information, and for example, all packets to a particular subscriber can be treated as belonging to the same flow in an SDN-enabled network. SDN-enabled IPv6 transition is a flexible, seamless, and future-proof solution for IPv6 deployment at any level.
Thank you very much. So I guess you demonstrated that we can use SDN in order to move to v6. The app that you have, you said it's Open v6. Is that downloadable? Anyone can download it? So.
Yeah. And for the Android version, it's already on Google Play. For the Apple version, it's waiting for Apple's App Store's approval.
Because so in terms of cost, you would need just a server, $3,000 server, and you can work with it.
Yeah, for this app, you can choose to different servers. It's up to you. Yeah, currently we have one server running in Santa Clara.
So basically for the SMEs that do not have the skills, this would be the ideal transition way of doing it.
Right.
That on the fly, you just switch it on, it works. You have v4 and v6. So.
Yeah, exactly. I have another talk this afternoon. I can show you the details.
Yeah, I saw the same thing with college students from Singapore that they have deployed the same thing, and they won the award for that. I was chairing that event last year. Mm-hmm. So I hope it's not the same students that maybe you should work with.
No, we have.
One question is we still have time because we started a bit late. So we are still, no, you seem to be all convinced. Anyone who's going to download the software right away? Or somebody's doing it now? No? I think you should do, and it would be an excellent contribution. Tina, thank you very much for
Thank
that
you.
excellent presentation.